So having understood this Hilbert fractal design, now suppose you want to generate an annular ring-like structure. Suppose from this design only, you want to generate an annular ring, which means you want to design a central hollow region. That means the central portion you see is basically a solid metallic patch. I want to cut out a metal. I want to cut out some portion of the metal from the central so that I can have a ring like. Suppose this is a ring which has this finger hole at the center. Like that, a design I want to create. Again, the Boolean extrude option will be used. Boolean subtraction will be used. But there will be a purpose for it. So first let us have the design. After that, I will explain the purpose. See, initially, I told you that the current is limited on the edges of the patch. Okay. See, the current is flowing like this. Just follow the movement of the cursor. Current is flowing like this in the step. Again, down the steps, up the steps, come here, down the steps, up the steps, like this. Generally, we won't find any current flowing through the central region. Okay, through the central region, there is no current flowing. This is the concept which we will be exploiting. First, let us create the design. So what we will do, again we will select modeling, extrude, escape, slot center. Let us name like this. Orientation will be Z only according to the discussions which we already had. Z min is 1.6. Height will be same 0.002. Now the x coordinate. See, this level is x is equals to -7. This level is x equals to +7. It will be better if I select this patch once again. See, I will zoom it also. This is x is equals to -7. This is x equals to +7. This is y is equals to +7. And this level is y is equals to -7. This. Okay. Now, again, extrude, escape, slot center. Z min is 1.6. Tab is 0.002. Height is 0.002. Now let us select x is equals to -4 somewhere here. Okay. Y is equals to 4. Suppose this here. Y is equals to 4 here. Tab 4. Enter. This point is selected. See where the cursor is now. That is the point. Okay. Now we will, from this point we will come to the right. So we are maintaining the same horizontal level. So y will remain 4 only. But x now comes in the first quadrant. So x will become 4. So 4 tab 4. Enter. Now we are coming here. Now we will go down. If we are going down, we are maintaining the same vertical limit. That means the x coordinate will remain same. The x coordinate will remain same. So 4 remains 4. Now y comes down to the fourth quadrant where y is negative actually. So y becomes -4. Where will that point be? Here. See where the cursor is? It is here. Okay. Now we will come to the right here. Sorry, we are coming to the left in the third quadrant. In the third quadrant, basically we are moving along the same horizontal limit. So y will remain -4, but x comes to the third quadrant where x is negative. So x will be -4 tab -4. Okay. Again, I am saying these dimensions are completely depending upon the situation. You can change it at your will. Okay. Now preview. See how the structure shows up. See, this is the structure. Okay. It is demarcated again. It is not cut out. Double click. Boolean, drop down, subtract. Slot center you select. And enter. See. Annular structure is defined. is determined, where there is a hole, I mean there is a metallic hole. The dielectric is always there. Let me select this component. See, dielectric is there, but the metal is not there. Question is why? Now the justification for this structure. See, I told you previously that the current always finds its way along the edge of this patch, like this, like this. Okay. The current never flows through the center. So virtually, the metal portion at the center is having no function at all because the current is not flowing. And these metals which are actually used in practical prototyping, it's copper, metallic copper, which is quite an expensive component. Okay. So practically, we will always want to reduce the amount of metallization in our structure. And at the same time, see, whenever there are metals, we have actually learnt it previously, whenever there is metal, there are always conduction losses involved. Because current flowing through metals, they dissipate energy according to Ohm's law. They dissipate energy according to the resistance of that metallic conductor. And so there is conduction loss. In terms of antenna design and performance, this conduction loss can severely limit the bandwidth of the antenna. So what is the option? What is the way out for reducing this conduction loss? If you are using a metal, conduction loss will always be there. What is the way of reducing it? The way of reducing it is to reduce the metal, reduce the amount of metal in the structure. Of course, without hampering the functionality. Okay. And of course, this metal at the center is not having any function at all because the current is not flowing. So we can safely remove it. So in terms of conduction loss also, in terms of cost effectiveness also, this may seem to be a very viable option. So this type of structural modifications we can also do. So today we studied about an entirely new domain of design which is incorporating fractal geometry. What are fractals? Why they are used for? What are their advantages? What are the types of fractals? We had an idea. The most popularly used fractal, which is the Hilbert fractal, we understood the dimension, we understood the geometry of that fractal, and then we tried to implement that Hilbert fractal geometry in the actual antenna design. We understood what effect it has and how it exerts the effect on the results of an antenna. That means in terms of enhancing the bandwidth of that antenna, how it contributes to that in terms of increasing the electrical path length of the surface current. We finally designed the Hilbert fractal antenna up to the second level of iteration and also discussed some basic requirements to implement fractal antenna, fractal geometry. That means in terms of same shape preservation, same dimension preservation, same order of iteration on all sides of the antenna, like these. Ultimately, we developed the structure. Finally, we concluded this design process in this session by cutting out an annular hole at the center of the patch, explained the importance of that in terms of the flow of surface current. As already mentioned, surface current does not flow through the center of the structure. It always finds its way along the peripheral regions. So the metallic portion at the center of the structure is actually having no effect on the result. So we can remove it. And as we are removing it, we can actually lower the amount of metallization, which helps us to reduce the conduction loss and also help us in maintaining the cost effectiveness of actual prototyping of the prepared design. Next time when we meet, we will actually simulate the structure and study the different simulation results and have a comprehensive analysis of the different parametric results of an antenna.